Okay, so in this section, we're going to be taking a look at solutions and some of the properties of solutions, physical properties. Also take a look at some chemical characteristics of solutions. So when we talk about solutions, we can define a solution as it's just another word for a homogeneous mixture of two or more substances. And we actually talked about mixtures, homogeneous, heterogeneous mixtures way back in at the beginning of the semester. So remember, in a homogeneous mixture, all it is where we have multiple pure substances that share the same physical space. They're not chemically combined, right? That's why they're mixtures and not compounds. Multiple pure substances share the same physical space. And the key feature that makes it a homogeneous rather than a heterogeneous mixture is the fact that the components are evenly or uniformly distributed. So the mixture looks the same throughout. Okay, and that is nothing more than what a solution is. It's a homogeneous mixture of two or more substances. Typically, we can define two components of a solution. So the solution, any solution, will be made up of two components. We're going to be seeing a solute, or we can have actually multiple solutes, a solute or solutes plus the other component of the solution, which is going to be the solvent. And it is important to note that the solution is the combination of the solute and the solvent, because it's very easy to get confused, especially with the solution and the solvent. There is a distinction between them. Okay, what is so the solution is the sum of the solute and the solvent. What's the difference between the solute and the solvent? Well, that has to do with the relative amounts. So the solvent is the component of a solution that is present in greatest amount. So what makes up the majority of the solution? That is what the solvent is. And then the remaining things would be the solute or solutes. So these would be the components of the solution present in smaller amounts. So as a very simple example, if you have a beaker and you have some water in it, some H2O, and you added a pinch of salt to it, and then you stirred it up to dissolve it, well, then what you end up making here, right, is you have a salt water solution. And we'll abbreviate solution as SOLN as our abbreviation. And in this particular example here, the solute would be the salt, regular table salt, sodium chloride, for example. And then the solvent is going to be the water, H2O. Okay, that's a very simple example of a solution. We've all made saltwater solutions at some point, or even sugar solutions. So we know what they are. And typically when we think of solutions, we normally gravitate, or we think about solutions where water is a solvent, typically liquid, water as the solvent. However, we can have examples of solutions where the solute and the solvent can be in all sorts of different phases. So the example that we just looked at, for instance, was having a solid solute, NaCl, in a liquid solvent like water, so salt water, for example. That's what we normally think of as solutions. However, we have examples like we just talked about in the last section. We talked about gases, right? And the air around you is actually a solution. It is a mixture, homogeneous mixture of a bunch of different gases um, where nitrogen is the solvent, is the main component, and then all the other gases there are going to be the solutes. We can have gases dissolved in liquids to make carbonated water, for example. Right, so here you have your CO2 dissolved in water. That's what makes it what gives it its fuzziness or fizziness, I'm sorry, CO2 dissolved in H2O. We can have a gas dissolved in a solid, right? So hydrogen gas and palladium, for example. We can have a liquid dissolved in a liquid. So for example, all your alcoholic beverages, those are liquid solutions. You can have a liquid dissolved in a solid. So mercury in silver, for instance. And then we can also have solids dissolved in other solids. So brass, where copper and zinc form a homogeneous mixture, that would be an example of a solution as well. So the point here is your solutions can exist in all states. They don't have to be liquids. They can be in solids. It can be gases as well. We can then take a look at our solutions and we can define or we can classify them based on how much of the solute is dissolved in a given amount of solvent at a specified temperature. And we're going to come up with 3 different ways to describe solutions based on that amount of solute that can be dissolved. We're going to talk a lot about how we can quantify the relationships between the solute, the solvent, and the solution as a whole a little bit later on. But for right now, we're going to take much more of a qualitative look at it. So in an unsaturated solution, what you actually have is a solution where we have less solute in it, in the solution, than the solvent can actually accommodate at a particular temperature, right? So this is a key thing here. When we talk about how much solute can dissolve in a solvent, we usually specify it at a particular temperature because the solubility of something is temperature dependent. Okay, the solubility of solutes in a solvent depends on the temperature. Okay, so when we talk about solubility, that term itself actually is a measure of the maximum amount of solute that can dissolve in a given amount of solvent at a particular temperature. So for example, we can say, I'm just going to make up some numbers, the solubility of NaCl in water is, and we'll just say 35.45 grams of sodium chloride can dissolve. We can dissolve a maximum of 35.45 grams of NaCl in 100 grams of water, or 100 mils. So in this case, it's a volume at, let's say, 0 degrees, no, 25, let's say 20 degrees Celsius. All right, so it tells this idea of solubility, tells us the maximum amount of the solute that can dissolve in a given amount of solvent at a particular temperature. And all of these are going to typically be grams per mil at a particular temperature, or depending on the units, they can be slightly different, right? So in an unsaturated solution, what we actually have is less solute than the maximum amount. So less than the maximum amount of solute dissolved. So in other words, we can add more solute and it will dissolve. Okay, that's an unsaturated solution. The solution can hold, in other words, it can accommodate more solute. We have a saturated solution. So in a saturated solution, this, you can think of it, analogy to these different types of solutions as a sponge, right? So you start off with a dry sponge, it's unsaturated, you can add more water to it, and it can hold it, it can accommodate that water. Same thing with your solvent. It starts off as unsaturated, you can add more solute, it still is unsaturated until we get to the point where that solvent has the maximum amount of solute that can accommodate, and we call that a saturated solution, similar to our sponge, right? We get to a point where we add enough water to it, and the sponge is saturated. If you add any more water to it, well, water is going to just come out of it, right? Same thing with our solution. We have a saturated solution. It has the maximum amount of solute dissolved. Okay, no more solute will dissolve. So if you add more, solute is added, okay, it will not dissolve. It'll just stay, in the case of the salt that we have here, it'll just stay as a solid down at the bottom. It's a saturated solution. It contains the maximum amount of solute. Under certain circumstances, we can exceed the maximum amount of solute, and that is called a supersaturated solution. So these types of solutions contain more dissolved solute than is present in a saturated solution. And they're generally unstable, inherently unstable by nature. And if you disturb them, okay, if disturbed, so for example, if you have this supersaturated solution here, right? So it contains, we can adjust the conditions such that it actually has more than the maximum amount of solute in there. If we disturb it simply by adding maybe a speck of dust to it, or just a particle of something, what happens is it causes the solid or the solute to precipitate out of the solution. And it usually happens fairly quickly, and the crystal, the precipitate forms as crystals, and they actually grow. And it's actually quite interesting to look at if you've ever seen one of these. It's a process, again, that happens because that supersaturated solution is unstable. And if disturbed, which is very easy to do because it's unstable, that solute, whatever's in there, is going to precipitate out of that solution.